students, welcome to lecture number 10. So, I hope you are able to understand the basics of material science. We are way behind discussing the AIML. First, we need to build up the foundation, then we can discuss about AIML, how to utilize that is the major important aspect rather for you. So, hence first have some patience and try to understand these basic aspects. So, today we are going to discuss electrical properties, but before that let us take a stock of the things which you have done in the last lecture. So, again and again I am telling you these aspects. We need to know very nicely or very importantly rather the correlation between structure and properties, and that correlation is only possible when you know how to connect processing with the structure, because processing is something which helps us to make components using different materials, and once you make it, we make certain kind of a structure or rather microstructure, and that in turn determines the properties. So, we discussed about mechanical properties in the last 2-3 lectures. Now, we will discuss about the functional properties like electrical, magnetic, electronics properties. So, electrical properties are very important because many of the materials are used in the world basically based on their good electrical properties. Most important example is copper, oxygen free copper, which is used as electrical cable worldwide. Why copper is used? What is the advantage of copper? All these things must be known, right? Because when we used copper, started using copper rather as an electrical cable, we never done any machine learning calculations to understand why copper, or rather nobody has actually did any design. The copper came into picture mainly because it is easily available, earth abundant, cheaper than many metals like gold and silver, and it has a reasonably good electrical conductivity. And another important aspect of copper is it can be made into different shapes, because copper, as you know, has FCC crystal structure. So, therefore, it has many slip systems. It can be easily deformed into different kinds of shapes, wire, rods, whatever you want. So, these all together gave copper the advantage, and that is why you cannot have a cable in the world made up of other than anything else other than copper. We cannot even think about it. Whether you will have graphene and other stuff which has come into picture recently, but you can't even dream of replacing copper by graphene as the electrical conductor. So, let us talk about a little bit about that. As you have understood that components are subjected to the service conditions. So, therefore, selections of material will depend on the properties which will allow you to match its properties with the service conditions, as well as the manufacturing process you adopt to make them, because if you cannot make them with any manufacturing process, then it is not of use. You will I will talk about it, maybe not be today, but next lecture. There are a lot of superconductors. They are fancy materials. They can actually reduce the electrical losses, transmission losses extensively, but they are expensive, and most important thing is it is not easy to make them in shape we want. So, therefore, manufacturing ability of any material is of paramount importance. If we cannot manufacture, it cannot be used. Well, we talked about mechanical properties, especially we talked about tensile properties, because material can undergo a lot of different kinds of stress or loading, like tensile loading, compressive loading, shear loading. We talked about it a lot, but finally, I discussed only tensile testing, because that is the predominant testing method used in the world for ductile materials. For brittle materials, we use compression testing. Compression testing is exactly done in the same setup as a tensile testing machine, but loading directions are different. So, material which are likely to be brittle or likely to show brittleness must be tested using compression setup. Tensile testing is no good for them. Tensile testing is useful for material which show ductility. This is a snapshot of the tensile stress strain curve. You can see here nicely the elastic plus plastic portion and the different stages of tensile testing for a sample. Then we talked about effect of strain rate, how strain rate can affect materials or strength of material. Strain rate is defined as a epsilon dot equal to d epsilon by dt, and there is a constitutive relationship which is given by sigma t equal to c epsilon dot to the power m, and sigma t is the tensile true stress, c is a constant, and epsilon dot is strain rate. M is what? Strain rate sensitivity. You have to understand one thing, this is a constitutive relationship like this one, sigma t is equal to k epsilon dot. These two are fundamental equations. They are widely used in modeling processes, modeling different materials. So, please keep in mind. And I showed you some values of m. M is normally very low, most of the cases less than 0.1, but there are cases where m can be go as high as 0.5 to 0.8, like in case of titanium 6 selenium 4 vanadium alloys, but normally it does not go very high, but there are few cases where it can go even much higher, it can go even close to 1. That is what superplastic deformation can happen. A material can be deformed extensively, almost like a 800 to 1000% increase of its original length possible without any failure. That is why the superplastic behavior comes into picture. Metallic alloys and some ceramics also show superplastic behavior, and we understand superplastic behavior is different from normal tensile behavior, but you should know this, there are set of materials which show superplastic behavior. Then I talked about a little bit about fatigue. Fatigue is more real life situations. There are vibrations in automobiles, aircraft, compressor, pumps, even swaying of bridges, buildings, all lead to fatigue. Fatigue is a word which is widely used by human. Sometimes I get tired, I said I am fatigued. So, fatigue means you have undergone cyclic loading, cyclic stress and strain, basically stress in human life. Stress is very common, and if this stress is positive and negative, then you started feeling fatigue. So, fatigue is exactly same. Materials are subject to cyclic loading, tensile or compressive or even both. This is what we discussed here. You have in the first case A, you can see the loading is changing from tension to compression, and there is a sinusoidal nature of variation of the load. In the second case, it is only tension, but the nature of loading is sinusoidal. In reality, the stress of stress or variation of the stress as a function of cycles may be much more complex. That is what is shown in C. You can see it in C, and this is what is experienced by an aircraft wing when subjected to periodic unpredictable overload due to wind gust, and this is very common, by the way. So, therefore, by the modeling fatigue is not an easy task, you have to understand. I have not talked about it different models of fatigue because of the time constraint, because of the discussion to be limited to certain aspects, but one can go to that book by George Dieter I shown you in the last class and understand how this is important. Fatigue is normally characterized by SN curves, stress versus number of cycles curves. We can determine the fatigue limit for ferrous metal very easily, for non-ferrous metal it is not so easy, just like yield stress in case of tensile testing for non-ferrous and ferrous. The last I talk about creep, right? Creep is time dependent high temperature deformation. Well, it can be room temperature also. Some metals like lead, tin, they show creep behavior at room temperature because their melting temperature is very low. Let us talk about shoulder alloys, which is used in the electronic devices, like in case of phones, mobile phones, cameras, or in case of computers or laptops or tabs, we use that. There the circuits are joined by shoulders, and we use a lead in solder still today, and therefore, they can undergo creep at room temperature. If you do not cool them, they may break even at a lower stress. That is what happens. Many of the circuits break down because of mechanical stress. It has fallen down if your phone might have fallen down on the floor and then starts not working, because some solder joints might have broken. So, therefore, creep can happen at room temperature also, but we are talking about creep in jet engines, that happens at high temperature. It basically happens due to high temperature deformation, time dependent deformations, that is why it happens. And we use super alloys for these kind of engines, and super alloy is a complex chemistry, as you know, you can see from here also it contains almost like a 10 to 12 elements. And creep is what? Tensile stress, if it is less than yield stress also, if it is subjected to a specimen at elevated temperature, it will elongate continuously until it ruptures. It is a long term phenomenon, important in design of steam or gas turbine engines, even aircraft. So, you understand that. And creep curve is like this, strain versus temperature at certain constant load. And this shows the 3 stages of creep: primary, secondary and tertiary. What is important for is that secondary creep. That is why the creep rate, which is nothing but epsilon by dt, is almost constant. And that is something which is we like to operate in that regime very clearly. So, if you want to have a low creep at high temperature, you need to have a single crystals, because creep is something which is governed by gain boundary sliding. So, better to have some kind of a single crystal without many gain boundaries, then it is possible to reduce the creep. And then I little bit discuss about stress and for the living cells, but again this work was done by Subha Suresh and the G. Bao long back 2003, but it is very important that we can understand that. Finally, we talked about physical property like density, melting temperature, specific heat and other things. Then I told you that this is something we will discuss later. Let us talk about a little bit more on these aspects before we go into electrical properties. As you know, if I plot, let us say if I have a liquid, ice, water, right, let us take if I have water. No, water may not be, let us take a metallic liquid, let us say pure copper, melt it down and then you are cooling it down. If I plot relative volume, volume per unit weight, as you cool down, this will vary like this. First it will drop and then there is a slope change. Why this slope change? Because if you cool rapidly to bypass formation of crystals or grains, then you will be able to freeze like a glass or amorphous structures. There will be small change in relative volume, but suppose if you allow the liquid to solidify by formation of crystals, and this will lead to formation of this will lead to generation of future heat of fusion, then this volume will drastically drop to a lower value. Well, that is understandable. Let us say density. Density is nothing but mass per volume, right? Density is nothing but mass per volume. So, crystals has higher density compared to glass, because crystals are more packed structures. We have discussed about it. Glasses are random, so there are more open structures. So, therefore, density of glass is lower than the density of crystals. So, mass is same, so that means volume should change, right? And for the crystals, volume is smaller, that is why they have a higher density. For amorphous structure, volume is higher, there is more free space, that is why it is that. So, now the question is, if I freeze a liquid to glass, volume, relative volume will not change much. It will change a little bit, because there will be rearrangement of atoms or relaxation of atoms once it become solid. So, liquid to solid, to when it freezes a glass, is demarcated by change of viscosity, nothing else. There are minute change of structures. At the atomic scale, there may be some small changes, but overall atoms will remain random or semi-random structures. So, that is what happens. That is why Tg is known as a glass transition temperature. That is the temperature below which a liquid is frozen to glass without formation of any crystals. So, now glass is very important material, right? I talked about metallic glass. These are the taken from Oak Ridge National Lab in US. These scientists have discovered a new bulk metallic glass, steel, bulk amorphous steel that is non-magnetic at room temperature and significantly harder than in the conventional steel. This is available in this article, you can see here, this is what is mentioned, you can go through. These golf clubs are made using ball metallic glass. I talked about it, right. For the golf bats you need high resilience, and resilience means what? Sigma y square by 2e. Sigma, the resilience is what? Resilience is something known as sigma y square by 2e. So, resilience is sigma y square by 2e. For the glass, both sigma y is very high and E also is very high, very steep. So, if you have stress strain curve like this, very steep, very high, even if it breaks little bit, does not matter. So, you have a very high area under the curve. That is what is called resilience R. So, glasses have that, that is why they are used as a golf club. They have a little bit of ductility also compared to the window glasses, that is another reason they are used. Silicate glasses, as you know, they have a based on the silica structure. So, basically this is structure of quartz. Quartz is what? SiO2, and a silica is basically it is like a tetrahedral structure. You have an atom at the center which is called silicon atom and 4 corners. You remember the tetrahedron, right? Tetrahedron is like this. Just now I shown you. This is a tetrahedron, and this tetrahedron is basically has a 4 corners, and there is a central atom. Okay, these are the 4 corners, and inside in the center of the tetrahedron you have a silicon atoms. That is what can be marked like this. Okay, this is silicon atom, this is the oxygen atom. This network actually forms all across the material, and this is a 3-dimensional network. That is the structure of the silicate glasses, and that is why silicon glasses actually, for the crystalline ones this network is very ordered. For non-crystalline or glasses this is random, that is the difference. So, you can either form silica which forms different kind of crystal structures, orthorhombic, retrogonal, and glass is like a random arrangement of that silicon tetrahedron. Well, there are different kinds of glasses. The one which is showed is this one, you see this is called Bristol glaze, which is used for the cups, and then you have soda lime glass, which is what is used in the window panes, and they are actually contents of sodium oxide, Na2O, COO, SiO2. This is sodium gas, and this is borosilicate gas which is used in the labs for experiments, pipettes, beaker, many things. And you have also vitreous silica. So, vitreous silica is 100% silica, that also can be glass, but that is very rarely used. Normally use a borosilicate glass or window glass. We can also use fiber glass, which are nothing but E glass. There you have fibers inside. So, this you see the chemistry is very important. Remember we talked about glass at the beginning, first lecture, to impress you upon why machine learning is important. Look at the chemical component of glass. It can be many: SiO2, B2O3, L2O3, NO2O, CaO, MgO, K2O, ZnO, PbO, many other things depending on the type of glass. To give our perspectives, we know toughened glasses. Many of these glasses on the car windows are toughened glasses. They have little bit of K2O. This K, a potassium ion, which is bigger than sodium ions, replaces some of the sodium ions and creates a surface compressive stress, and that makes it tough so that it does not break. Please go back to discussion the toughness, how the toughness is defined. So, tough glasses are very important. Even if you give a punch to the glass, it will not break. So, that is about the glasses and other things. Let us talk about a little bit of electrical properties. Remember, glass is very important component. That is what I thought I should spend some time. Well, electrical properties means what? You have to differentiate between conductors, semiconductors, insulators. And if I take a single structure, high tension cable, this is a high tension cable structure, I can see all of them. This cable is conductor, it conducts electricity. This is an insulator which is making this cable separated from this structure from this this steel structure, so that even if high voltage is passed through this cable, this will not make this steel structure conduct electricity. That is why this is basically ceramic. This is a porcelain ceramic which is used for this. You must have seen this kind of things when you go on the roadside, when you see these high tension cables. These are very widely observed. So, you see in the same structure we have insulator, conductor both present. Semiconductors we will talk about a little later. This is what where semiconductors are very widely used. Okay. This is taken from this website silavaco.com, and they are actually producing this kind of chips, silicon chips. And as you can see, the structure is so complex. So, you have silicon semiconductor, this kind of different kind of structures are built up. I do not want to discuss about a lot of these things. You can see different kinds of things that use silica, polysilicon, okay, tin, tungsten, TUS, aluminum, even say aluminum, copper, silicon nitride, all are used. This is what is, say here silicon is a semiconductor. So, it is all about electrons in solids and their ability to move around within the solid, that is what it is. In case of mechanical behavior, it is all about defects, point defects, line defects or surface defects. Here it is all about electrons. So, do you have electrons free floating around us? Do you think in air? What do you think? Obviously not. Electrons are not freely floating in air. If it was that, then air could have been conducting electricity like anything. It would have been very difficult to live in this world, because you have electrical wires around it. They could have simply made the air charged, and that could have affected our human life. Unfortunately, air is not conductor to electricity, but that is probably one fortune for us. So, electrical conduction is given by what? Ohm's law, and it is classical Ohm's law. It is taught in school physics. Now, V is equal to I into R. V is the voltage drop, and that is nothing but J by C. J is the current density and C is the coulomb. That is equal to current, which is in amps, nothing but coulomb per second, and R is the resistance. R is basically a constant, and this is called ohms. The resistance unit is called ohm. This is called a Ohm's law, because that was discovered by Ohm. And then we can always convert the resistance into material property. That is called resistivity. So, resistance is not a material property. Resistance can depends on many things, like it depends on area, depends on the length of the wire. So, if I talk about resistivity, it can be like this: rho is equal to R into A by L. So, A is the area and L is the current path, flow path, that is the length of the wire, we always talk about it. And this rho is independent of anything, it is basically material property. And we can use this to differentiate between conductor, semiconductor and insulator. So, we can always define conductivity. Conductivity is nothing but 1 by rho. So, either you discuss this electrical conduction in terms of rho or in terms of sigma, which is, so remember this sigma is different, this sigma is not same as the stress, this is the electrical conductivity. Well, to give you perspectives, let us talk about values of conductivity. For metals, metals are highly conducting to electricity. So, they have a high value of conductivity, units ohms meter inverse. So, you can see copper 6.0 multiplied by 10 to the power 7, massive electrical conductivity, compared to silver, silver is hardly 6.8, nothing much, right. So, why you will use silver? Copper is cheaper, widely available, and it has almost close to same. Iron has quite a bit less electrical conductivity. So, that is why iron is not used. Steels are not used as a cable. If steel could have been used, though, it was much cheaper, but copper is used because copper has much higher conductivity. If you consider semiconductors, silicon I told you, right, germanium also will be semiconductor because they comes in the same column of periodic table. Silicon has a conductivity of 4 × 10⁻⁴. You can see almost 11 orders of magnitude less. Germanium is better, but 2 × 10⁻�0. Gallium arsenide, which is a compound semiconductor, it has even much lower, the 10 to the -6 meters. So, that is what it is. These are all taken from Callister's book. Selector values are taken from book of Callister and Red Switch, if you can refer that. What about ceramics? Well, just now we talked about soda lime glass. Ceramics has a conductivity of 10 to the power -10 to the -11. Concretes 10 to the -9. Aluminum oxide 10 to the -13. What about polymers? Polystyrene, which is we are using as a material for our shirts, 10 to the -14. Polyethylene, which is used as a power pack or pouch in everyday life, 10 to the -15 to -17. They are all insulators. They do not conduct electricity. So, you know now the values, you know that how to differentiate them. Well, let us stop here the part 1 of the lecture, and we will talk more about this in the next part. Thank you.